Hi, I'm Surya, and I'll be presenting our paper SENT-MAP, Semantically Enhanced Topological Maps with Foundation Models. Robots operate in a wide variety of human spaces, but they are more commonly seen in structured environments and less in unstructured complex environments. This project aims to explore a way to enable robots to operate in unstructured environments and perform long horizon mobile manipulation tasks. Classical representation methods are merely a way to reconstruct the environment and don't represent the context. Therefore, they are not interpretable. Hence, we introduce semantically enhanced topological map to address this issue. Further, long horizon task planning requires generalized algorithms that adapt to different types of data and scale well with increase in data. Therefore, we use foundation models to tackle this problem. But to execute the plan in the physical environment, an agent capable of navigating and manipulating is required. Our choice of robot is Spot from Boston Dynamics that is used to interact with the physical world. Let's look at each of these components in more detail. Topological map is a graph where each node represents places or landmarks or any meaningful location. Further, each node can contain additional information to represent the semantics, whereas edges represent the connectivity or traversable paths between them. Hence, this form of representation makes it both scalable and interpretable. Using this, the robot can now represent the environment. Foundation models are large pre-trained models that serve as general-purpose backbones. They are trained on a wide variety of data and can operate on different kinds of data such as image, text, audio, etc. Due to their high generalization, they can be adapted to any task without fine-tuning or with minimal fine-tuning. Some famous examples of foundation models are ChatGPT from OpenAI, Llama from Meta, and Gemini from Google. Now that we know the components, let's look at the framework. The framework operates in two stages: the mapping stage that produces the sent map, followed by the planning and inference stage that uses the sent map. Let's look at each of these stages in detail. The mapping stage. In the mapping stage, the first step is the operator guiding the robot through the environment, showing it various locations. At each of the locations, the robot captures the environment as a RGB image. This image is then passed through a foundation model. In this project, we use Llama 3.2 90 billion vision instruct model that understands the image. It then extracts meaningful information from the image to fill out a predefined template of a sent map. Let's look at the sent map. The predefined template of sent map is a hierarchical map represented in JSON format, making it human interpretable. At the topmost level, the navigation node represents traversable waypoints in free space. Each navigation node may contain semantic nodes such as table, cabinet, etc. The operator shows the robot these semantic nodes that the robot captures pictures of. These semantic nodes can further contain objects such as mug, headphone, toy, etc. Objects can include metadata. These objects are targets for high-level tasks. This hierarchical structure allows foundation models to reason over both spatial and semantic aspects of the environment. Many such filled templates are first human verified and then stitched together to form a scene JSON representing the entire environment. Let's look at the inference stage. In the inference stage, firstly, the user sends a text-only query to Planning FM, which is a LLM capable of handling text such as Llama 405 billion, Llama 8 billion, GPT Mini, and Gemini. The Planning FM uses the scene JSON, which is a collection of sent map, to produce a sequence of low-level actions such as pick up an object, move to node, place the object, etc., to be performed by the robot to accomplish the task. To evaluate the performance of the framework, we tested on three different object retrieval scenarios. Scenario 1. In this scenario, the user asks the robot to retrieve a sponge. The sponge is placed in logically and semantically appropriate location, that is, in the kitchen by the sink. In scenario 2, the user asks the robot to retrieve coffee powder. The coffee powder is placed in the office rather than in the kitchen, which is not its common location. In scenario 3, the user asks the robot to retrieve a tissue box which is present on the table in the office, but many other locations also contain tables, hence introducing ambiguity. The planning FM then produces a sequence of actions to accomplish the task. Here we can see that the robot for scenario 1 is correctly able to navigate to the kitchen sink and identify the sponge. In scenario 2, it can be seen that the robot is correctly able to go to the office table to retrieve the coffee powder jar instead of the kitchen, which is the usual location. In scenario 3, it can be seen that the robot is able to correctly go to the table that contains tissue box, even though many other locations in the environment contains a table. This shows that by using ScentMap, the planning FM is able to accurately reason over the environment. Through experimental verification, it can be concluded that ScentMap is a very robust way of representing the environment. It enables FM to plan accurately even with ambiguous user queries. It also works well with small locally deployable FM. In the future, as foundation models improve, this method would also improve. Thank you.